Okay, great. Hi, everyone. It's my great pleasure to introduce to you Professor Vittorio Ferrari from the University of Edinburgh. He's an associate professor there and leads the Calvin group. Vittorio received his PhD from ETH Zurich back in 2004, and his work has been very well known in the CVPR, ICCV communities. Today he comes to give a talk to us about his work on large-scale object localization in ImageNet. Take it away.
So thank you, Raul, for the introduction. So let's start by chopping off my title. I thought it was large-scale because we got these 15 million images, and we annotated 1 million of them with pixel-level segmentations, and was all excited. And then I came here, and yesterday morning, people showing up casually saying, "Oh, we run this on 50 million YouTube videos." Oh. So, let's say large scale, but maybe not Google scale, okay? So, we want annotations. That's the concept. We can't just have images which are labeled by the class they contain. That you can do some stuff. You can do image classification. You can maybe do some nice generic unsupervised learning. But many computer vision applications need object location annotations. Typically in the form of bounding boxes or even pixel-level outlines. These are necessary for object class detection, so training models that can then localize objects in test images. It's necessary to train models that can segment the foreground accurately, tracking in video, even for post-estimation of objects or humans. This type of object location annotation are really fundamental. So where do we get some? Yeah, can you give me some? Well, these are 3 of the larger standard data sets in computer vision. 20,000 images, 16,000 images, 15,000, you can crunch a bit, but I am still hungry. And I'm sure Google is too. So, enter ImageNet. That was big help from Stanford, Thank you, Fei, if you're listening. This is a large-scale database with 15 million images over about 20,000 object classes. Every image is put inside a semantic hierarchy. And every node of the hierarchy is labeled by the name of the main object it contains. And here is a compressed version of the hierarchy where I'm going down just one line of the tree. So you have entity, which is the mega root. Then you have basically these joint trees, instrument, plant, animal. And then you can go down this tree in instrumentation. For example, you have transportation, and you can go down and have boats and sailboats, etc. So when we saw that, we thought, yes, 15 million, now it starts to be serious. Unfortunately, only 7% of these images, maybe now it's up to 9, but not that many images, have a bounding box annotation on the object. So that's, still about 1 million images, so it's still something, but it's not a lot. It's less than 50 million. But what is most sad is that 0 images have segmentation annotation. So that's not enough. And this brings me to the goal of this project, which is to try to automatically add many more annotations to ImageNet. So we try to populate it with bounding boxes around objects, or even better, in the second part of the talk, populate it with pixel-level foreground masks. So the general idea is that we're going to try to transfer knowledge from certain source classes for which we have bounding box annotation. We're going to transfer it to other related target classes which do not. And these are some results, examples. We are going to come back to them in the result part of this talk. And then once we go for the segmentation part of the talk, we are also going to use as a source an external data set, the Pascal VOC challenge, because doing the transfer is a fun idea, but you cannot transfer from 0. You need to start from some seed. So in the second part of the talk, we're also going to use the Pascal VOC data set as a source. And here are some example results. So off we go with part 1. Where the objective is to populate ImageNet with bounding boxes. This is work that appeared at CVPR 2012. So one important part is that we want to be able to automatically select what are the source classes that are going to contribute their knowledge to the target class to be annotated. So now I'm going to use the schooner here as the target class. And its sources are going to be all its siblings of schooner, which are going to provide class-specific knowledge. You see, these are other boats that are kind of like schooner, not quite identical, sailboats and galleon. And we are also going to have one source, which is a generic ancestor. This includes all the classes that are above the schooner till the top of the tree, and all their descendants, but of course not including the schooner and its descendants. So anything else basically is the ancestor. And we are only going to use the images for these source classes, only those images that have the bounding box. So some images that don't, no, we don't care about in this part of the talk. So how is the general scheme of this knowledge transfer? So we are going to have a target image, which is an image of the target class for which we don't have a bounding box. We are going to start by sampling a small set of windows likely to contain objects. In this case, we use the ObjectNet sampling that we developed in 2010. You could also use other samplings. We're going to talk about this later again. And then you take your source classes, and for each type of source, so an ancestor or a sibling, we are going to train a model that conveys some knowledge about the appearance, the location, and the appearance context of the class, so the background of the class. And each pair of model source and type is going to be used to evaluate every single window in the target image. It's going to, for example, if you have the sibling class Galleon and you have its appearance, it's going to try to ask for every single window in the target image, is it a Galleon or not? And it's going to score a little bit higher on schooners and a little bit lower somewhere else. So because we're going to score every window with every pair of source and type, every pair of source and type leads to a probability distribution over the windows in the target image that tells you how likely it is that they contain the object according to this knowledge source and type. So any of these is imperfect. It's not going to localize the schooner perfectly because otherwise it would be a schooner model, and it isn't. But this probability distribution that it induces reduces the location uncertainty. This is the key word. We are going to reduce the location uncertainty in the target image, which will allow a later process to localize the object. So we are going to combine all of the pairs of source and type in a certain framework so as to maximize the location accuracy of the most probable window in the target image. Then we are going to select it, and then we do the classic game of having selected a window. We are going to train a detector for the schooner, then rerun it on the target images to improve the localization of the schooner iteratively.
Quick question. So the aspect ratio of these things you sample, is it constant? Is it vary?
No. The windows on which the game is defined, the ObjectNet windows, have an arbitrary aspect ratio.
They do, okay.
And all the models that we're going to transfer, they can be evaluated on any window. And in fact, you will see one of the models will be a distribution over aspect ratios. So it's going to say if he likes that window according to his aspect ratio. So this is the general scheme. That's the general flavor how we think that we can use the source knowledge, which contains the bounding box, to try to help localization on a target image without bounding box. So now we can go into slightly more detail. We said we have three types: location, appearance, and context. Let's start from location. So the target image in this case is this police car. Its siblings are vans and trucks and other types of vehicles with wheels. We take only the images which have a bounding box. And as location model, we are going to train a distribution over the aspect ratio of the siblings, a distribution over the scale of the sibling, a distribution over X, a distribution over Y. We'll have plenty of distributions. Then these distributions can be used to evaluate the windows in the target image, as we said, and this derives a distribution over windows in the target image. So you see, knowledge comes this side, it forms a location model, the target image sends its windows to the location model, and they get scored, and you get this distribution, probability of a window in this image, given the sibling location knowledge. The ancestor type provides the same kind of knowledge, just different distributions, because ancestors are distributed differently as siblings. So now we get to the appearance type of knowledge. So again, we take the sibling bounding boxes in this example. This time we also have negative bounding boxes. Before, for location, we only needed positive ones. So we just sample bounding boxes from the positive training images so that they don't overlap with the object. So this makes sense because the appearance model is only going to be run on target images that do contain the target. There is no concept of a target image without a target in ImageNet. This is not a Pascal detection challenge. And as an appearance model, we are going to train standard descriptors, a linear SVM on hog, a chi-square SVM on bag of surf, and a chi-square SVM on color histograms. So it's very traditional. After the SVM has evaluated the windows in the target image, we are going to, in a validation set, we are going to fit a sigmoid to them with plus scaling so that we can get proper probabilities out in order to produce this map. So the appearance transfer, this was for the sibling source. Now we said we also have an ancestor source, which is basically everything else in the tree. up to the root about your class. And for this type of source, because it's so generic over many classes, we found that a better appearance model than traditional hog is better to use objectness. So objectness, it's a generic window scoring function that tries to assess whether a window contains an object of any class, as opposed to amorphous background windows. So it could be a cow, a telephone, anything that has a closed boundary and appears a bit different than the background, as opposed to background which would be like homogeneous texture, sky or water or grass. At the midway through the talk, I'm going to give more details about objectness and advertise a little bit more. And we are going to train an objects model for each separate root of ImageNet, so that we can use the appropriate model for every target class without overlapping with its training data, so that the setup is, let's say, machine learning kosher. Once you have the objectness model, it evaluates every window in the target image, and boom, you get a distribution over locations in the target image. So this brings us to the third and last type of knowledge we transfer. So we had location, we had appearance, and now we have context. So by context, we mean the appearance of the pixels in the sibling images, which are not on the object. So this is an interesting idea, in my opinion, because siblings often occur against similar background. Let's say a cow and a horse, they're both often on grass. And the background appearance sometimes shares better than the object appearance. Because although cow and horses are kind of similar, the grass against which they stand is identical. So grass equal grass, cow kind of equal horse. And in fact, we found out that context transfer is really helpful because of this reason. But you gotta be careful. You gotta train a context model without using the pixels inside the positive training images, otherwise you're kind of biting your own tail. So this is the solution we came up with. We take random sample negative windows from the siblings, and we cluster them into prototypes. Here are the prototypes, just to reduce a bit the data. These are typical backgrounds. And now what we do, we are going to try to place all the other windows in the sibling set. Now they are labeled by positive and negative in the siblings, and we can see where they land, how close they land to their closest prototype. And it is that to learn a distance function threshold per prototype that tells you if you're closer than this to the prototype, then you're very likely to be background. And if you're farther than this from the prototype, then you might be foreground. And the reason you do this is that because the feature space is highly non-homogeneous, it so happens that a few bad background prototypes attract most of the correct object regions. Most of the vans, they land near a certain particular background pattern. And you want to downweight those prototypes so that your novelty detection engine you're trying to build works. So in the end, when a new window comes in from the test image, you match it to the prototype, and you check how close it lands to the closest prototype, and the distance to the threshold gives you a sigmoided version, gives you a probability. The important point of this mechanism sounds a bit complicated. The important point is that no information about the appearance of the siblings themselves, the vans, is entering the process, only to determine the thresholds, but there is no appearance model of them. That was important so we can decouple the information that comes from the appearance type and the context type. So this brings me to the end of the knowledge sources and types. Now, for every pair of knowledge source and type, we have obtained a distribution on the target image, on the location of the object. So how can we combine them optimally? So a good idea would be to try to combine them so that the distribution gets sharper. So the combined distribution has a lower entropy than the input distributions. So here we propose a simple combination model, which is a log linear model. You log your probabilities and you sum them all up according to a certain alpha weight. And the question is, which alpha weight? How are you going to train the alpha weight? So because we want to train the alpha weight so that it's useful for our task, the target function, the objective function is this one. You want to find the alpha so that the highest probable window after the summation maximizes the location accuracy of the target class. So if you have a few training target classes where you know you have the bounding boxes, you can pretend having an alpha vector, run the summation, taking the highest score window, and you can measure its overlap with the ground truth. And if it's high, this is a good alpha vector. So, of course, that's a well-set objective, but how are we going to search over alphas? Well, it so turns out that because there are max inside the summation, and because the number of windows is finite, this is not even differentiable. So that's not good. So instead of the exact argmax here, we're going to use a softmax, which essentially replaces the objective. Instead of saying the highest score window should localize the object well, the objective changes and says the expected overlap under the distribution of windows should be good. Right? We're replacing a maximization with an expectation, basically. And at this point, you have a differential objective. It's still not concave, but at least you can do gradient ascent. Not descent, should be ascent. You can do gradient ascent starting from some point. We start this gradient ascent from a regular grid on the simplex span by alpha, and then take the best result. So the attentive listener will have noticed that I'm using ground truth data on the target images, which would be forbidden, but of course at some point you've got to run your machine learning machinery. So what do? We learn the alpha on the other ImageNet tree to keep the setting kosher. So this is the alpha for the instruments is going to be trained on animals, and the alpha for animals is going to be trained on instruments, so that the setting is so that the machine did not see its test data. So at this point, we have this combined distribution. We can localize objects just by taking the most probable window in the combined distribution. And now we do a classic last engineering step. What do? You take the bounding boxes that your transfer process localized. Here's just an example. And then in each, now you can learn an appearance model targeted for that target class from these initialization windows. In this case, we train a Bagos-Surf chi-square SVM because you can run it on an arbitrary aspect ratio, so it's very convenient. Then you can add this as a new term in your combined distribution and reselect. This basically goes from here to here. So only transfer and transfer plus your class-specific model improves localization, as many, many others before have observed. And actually, I heard this trick from Google itself yesterday. So why is this a good process more on a theoretical level? Why would it improve? Why would it do better? Well, because the process of transfer looks at a single target image at a time, whereas this process looks at all the target images jointly. Implicitly, the target images are talking to each other through the fact that you have now a shared appearance model. So if in 70% of your images you got the TV correctly, and in 30 you got it wrong, your chi-square SVM you train is still liking TVs more than non-TVs. Then when you use it to relocalize, it snaps on the TV, even in the images where initially you had the wrong result. So this is the pipeline. At that end, we evaluate. So one issue is about making this fast enough. So the experiments I'm going to show you are 500,000 images. There are 1,000 windows that we use per image. So that's 500 million windows. That's large scale enough for us, and it's large scale enough to crack our cluster. So you need to do something to keep the data small and to keep it fast. Often we need to recompute window descriptors because they take so much disk space, we don't manage to store them. So one thing that we found very useful is spending some time in engineering your descriptors. So we implemented a fast extractor for histogram of gradients that work on a 2D aspect ratio scale pyramid as opposed to the original aspect scale only. So you can run it on arbitrary windows very efficiently. And you also can have some engineering tricks to get the Labensurf histograms very fast. And the solution is not integral histograms, but it's another trick. But because of time, let me move on. And the one thing I think that really made this project possible is that you can use this trick by Vedaldi and Zisserman called explicit feature maps, which allow you to compute the chi-square kernel at a cost which is roughly the same as the linear kernel. That makes a really big difference, because you really get the accuracy of chi-square at the price of linear. And then one thing you will have noticed is that the localization process basically is almost completely based on single target images. There is no communication between them until the last step. This also makes it very parallelizable. So just a brief word on related work on transfer learning and where this work falls in that landscape. So in fact, there are a number of works that try their best to use information from related classes to reduce the number of examples necessary to train a classifier for the target. And they fall, in my opinion, right in three types of categories. So many works transfer the parameters of the source model, and they use it as a prior for the target model. And that's possibly the most common form in the vision literature. So there is some more recent works that I think is very exciting, which instead transfer knowledge across an attribute layer. So instead of directly transferring parameters, you say, my class model is something like a function of attributes that I run. The attributes are like adjectives, striped, pink, and square. You run those first, and you use that layer to train your appearance model for the class. And then what you do, you don't transfer directly that model, you transfer the representation of the attributes, which allows you to save training samples. So that's a more recent trend, which I like very much. And then Another third group of works tries to transfer object parts, which is particularly relevant for part-based models, such as the DPM by Professor Ramanan, and also little shapelet parts. So in fact, the goal of most of these works is to reduce the number of examples necessary to learn the target. Instead, in the project I'm showing you, our goal is slightly different. We want to reduce the degree of supervision necessary to train the target. We want to go from bounding boxes to image labels. The number of samples to learn the target, there are still a lot. We use all of ImageNet. It's about reducing the degree of supervision. Because the goal is different, we ended up designing something that transfers another kind of knowledge. So the source class are not going to give you their parameters directly or their attributes. The source class are used indirectly to induce a distribution over windows in the target images, which reduces the uncertainty in the location of the target, and that replaces the bounding box annotation. That's a view on this work. And in fact, we had a previous work in 2010, which had a similar philosophy, and this is essentially direct extension of that. In that work in 2010, ECCV, the unary potential, we are using only objectness. We didn't have all these new sources and types, and we had a very heavy model that had a lot of pairwise connections that made it very slow. So what's new here is that we have more sources, more type of knowledges, and it's a lot more efficient. So because we believe that we're building on our own previous work, we ran an experimental comparison because, reviewers said, well, now it's more efficient, but you no longer have this communication between target images until the last step where you train the appearance model. So maybe you lost something. But in fact, yes, you do lose something, but it's more than compensated by the knowledge you get from all these closely related sibling classes. And because we cannot run this fully connected pairwise conditional field we had in CV10 at the ImageNet scale, it's just no way. We did an experiment on a much smaller subset with 10 random classes, and we hacked down the number of images so that it could run. And the net effect that our model is, even when running on 10 times more windows, 10 times more images per class, is still 10 times faster. So at the same level, it would be hundreds of thousands of times faster, and it does a bit better. So knowledge transfer does replace the need for pairwise potential to a good degree. So now this was more like a checking if we made progress with respect to ourselves, but maybe more interesting is now to see if we can solve the mission. And the mission is populate ImageNet. We want 15 million bounding boxes. Well, here I have 500,000. It's better than nothing. So we took 220 target classes, which have some bounding boxes for themselves and for their siblings. The bounding boxes that are present on the target classes, we ignore them. We keep them out so we can evaluate the method. Right? Because if we really run it on images that don't have any bounding box, then we don't know if it works. So, and in total we have about 500,000 images, and about 12% of them have bounding boxes. And every time you have a target class, you don't look at the bounding box for the target class, you only use it for evaluation. We consider a detection output by our method as correct if it overlaps with the ground truth more than 50% according to the intersection over union criteria, which is the standard in the Pascal VOC challenge. So here is to get a feeling for how difficult ImageNet really is, because there is some rumor spreading in the community that all the objects are centered and it's super easy. And my friend Olga Rusakowski got really mad at that, and she made a nice analysis. And in parallel, we made the same analysis, so we have 2 independent sources confirming. And this is an analysis of distribution of the size of the ground truth boxes with respect to the image area for the 62,000 we are using. And here is a visualization of how it looks. So some images have 100% over the bounding box is the size of the image, so that's easy. And then here is basically what you see. It's a uniform kind of distribution. There is quite a lot of images that are very small objects, like you can see here, overlapping less than 10%. Quite a bunch of images that overlap between 10 and 30%. Here are examples. This is a 10% overlap, 20%, 40%. And then, of course, there's quite many images that overlap 60, 80 or more. But because the distribution is rather uniform, this means that you still have hundreds of thousands of images which have small objects. And so this dataset is interesting. If you want more analysis, you can go on Olga's website. She'd be happy to. I
showed also done an analysis of the center bias.
Yes, there is that Olga made. I did not do it, so I'm just reporting the analysis we had. So here are some qualitative examples before we get to the quantitative. Here are some example results from some few of the 220 classes we ran this on. And the first row is to show some reasonably easy examples where our method works well. This red is a bounding box software method. The objects are reasonably centered, but big variation in appearance. The second example is to show you can get also very skewed aspect ratios to answer the question Rahul had. So the system is agnostic to that. It adapts to the aspect ratio that it needs to take. And in order to illustrate that at a certain point visual variability is so huge that even for human it's a problem, I would like to challenge the audience to tell me which class is this.
Platypus?
I don't know. Anybody who says Platypus?
I think it's platypus.
Something like that.
Platypus.
Yeah.
We have a consensus on Platypus. Maybe it's right. Who knows? And what is this thing?
Ferret?
Ferret.
Ferret. Okay, English speakers probably. Still, you had to think. You had to think. Okay, here are more examples to show that our method is also able to find small objects like TV monitors. Notice if there are two TV monitors, it's going to give you at best one, either 0 because it fails, or 1. It's not going to give you both. And street lights, and then this nice image with this candle. The detector prefers the candle. And here a soccer ball and the television. So it's to show it works also on small images. And here are some interesting failures. I find the failures very telling because they not only reveal the limits of our algorithm, but they also reveal the limits of annotation. So this is a classic failure. When you have multiple objects of the same class in ImageNet, typically only one is annotated, sometimes two. In this case, we picked a balloon, just not the right balloon. Too bad, we penalized our problem. It's our problem. So if you have a herd or a group of objects very close together, typically your method returns a bounding box on the group, which is not, strictly speaking, is not correct, but it might still be useful. Here is very fun. On basketball, we really have a problem. Basketball indicates the ball, but plenty of images are about Shaquille O'Neal and all the others with the ball interviewing, and the face recurs even better than the ball, so we get the face out. And sometimes it's a bit inaccurate, like you get rabbit and nearby object of the basket here. So here is a quantitative evaluation. So what you see here is a bit compressed. I'm going to just summarize a few directions. What you see here is the localization accuracy as the average intersection over union over all of the ground truth data. So this is not correct detection, it's intersection over union average, which is smoother. And here are the 3 types of knowledge: location, appearance, and context for both sources. And it's a lot of numbers, but basically the story is that the sibling is always better than the ancestor knowledge. No surprise, but that's what we find out. Siblings are more related, they contribute more. And in the case of the location queue, so important is the location prior that you can transfer from other classes. Scale and aspect ratio are even more important than location, which makes a lot of sense given that the space that they cut is bigger. In terms of appearance cues, the surf histograms turned out to work best. And then here is the advertising. Objectness alone is already doing a lot better than all the location priors. So it's a really good generic object detector. And context, and the context queue that I was advertising, is really contributing independent knowledge from the others. In fact, what you notice from this table, if you look carefully, is that every combination of cues improves over either component alone all the time. So in the end, if you want to do localization on a single target image at a time, you get to IOU average of 54. And if you then train an appearance model for the class and you do this iterative trick with the target, you improve by a little bit more and you get to 55.4. So the final target specific appearance model does help. So now 55.4, we have been told that doesn't sound so high. And I was answering, yeah, it doesn't, but it's not uniform. It's not every image at 55.4. It's the average over all the images. And this is a plot, the distribution of accuracy and localization versus all the images. And the largest peak is at 80%. And to give you a feeling, 80% is this example where red is ground truth, green is our output, or the other way around. And it's so close to perfect that, in fact, it's very useful already now to train object detectors. There are about a third of all the images have an accuracy of 70% or more. So they're very accurate. And about 61% are correct according to the Pascal criterion, which is already quite accurate. So the conclusion from part 1 is that it is possible to populate ImageNet with bounding boxes. Yes, good. Knowledge transfer does help localizing objects. It's not just about location priors. It's not just about objectness. You do need all the components. So far, we released 500,000 bounding boxes on our website, and we hope to get to 15 million within a few months, as soon as we can crack it. And the next question that would come in this line of research, for which I have no answers today, is that, well, now, okay, we got to the point where we produced these bounding boxes reasonably accurate. How good are the object detectors you would train on them, right? That was the dream at the beginning, so we just don't know today, but we might know soon. So just a few minutes on advertising the objectness measure before we go to the other part. So I was saying that this is one of our sources of knowledge transfer, which is generic over categories. And in fact, what this measure brings you is that for every window you can get a probability, a number 0, 1, that decides how likely it is for that window to cover an object tightly, regardless of its class, as opposed to background. And this gives you really a strong prior, I mean, it's not really a prior, it's a likelihood, but this gives a strong bias towards object, away from backgrounds. Here is a visualization. If you color every pixel by the average strength of objects of all the windows that pass by it, you can see that you can try to visualize it as if it were a saliency measure. You can see that it's strongly attracted by objects, and it's attracted away from background clutter. So I really want to show this example. I love it. So here is an airplane image, fairly easy. Objectness has a strong peak on the airplane, that's good. And a second strong peak on this. What is this? What is an object? Well, it could be a fish flying in the sky. It's a poet moment. That's equally an object as the airplane. So just to give you a feeling of what you get. But you don't get stuff on the road down here.
Sun is an object too.
Sun is an object too, yes. There you go.
Sunshine
is an object. It shouldn't be discarded by any saliency measure. Okay, the last thing I wanted to say is that you get this at a moderate computational cost of 4 seconds per image, so you can use it on a large scale. And the code is available online. It has been used in a number of applications so far, and I would love if Google uses it for yet other applications. So we get to part 2, which should be faster, where we try to localize objects up to their boundaries. So we want to produce a pixel-wise segmentation of the images. So this is more difficult in theory than localizing up to a bounding box, because just the space of possible segmentations is larger. So in fact, just to put things in context. One thing that got us excited is that there is no material to bootstrap from. There are 0 manually annotated segmentations in ImageNet, so we needed to come up with some other scheme. And the scheme is, well, there are segmentations somewhere else. We start from the ground truth segmentations of the Pascal VOC challenge. It's only about, in VOC 10, it's only about 1,000 or 2,000 that are manually segmented. It's a small set, but it already gives you some bootstrapping. We are going to use all the available information that's available to us this time. All the bounding boxes in ImageNet, the segmentations external. We are going to use the object class name through diffusion in the semantic hierarchy. We are going to segment images jointly over their class, so that we can share appearance models between different images of the same class. We are also going to transfer appearance models across neighboring classes in a similar fashion as we did before, so that we really have all of the available information to help us do this task. So here is a visualization, a high-level overview of the scheme. So we are going to recursively propagate segmentation from our initial source set to some images in ImageNet, and then recursively up to neighboring images. The idea is that the images we segmented before, which we call the source, we are going to help segment in new images, which we call the target. And this act of helping segment, we call it the segmentation transfer process. We are going to proceed recursively, which gives you a propagation. So the key idea is that if you have already a segmented image, this reveals some notion of how the appearance of the foreground and background relate. And if you then try to segment images of related classes, that's going to help segment those images. So here is how the recursive propagation works. We start from the source, and the source external, Pascal, and we jump into the easiest images. So this is the whole spirit of the work. Do the easiest thing first. What are the easiest ImageNet images? Obviously, they are the images which have a bounding box, because this constrains the segmentation. So we start from Pascal challenge, and we jump into any target. It could be, I don't know, a one-cell animal, and we transfer from motorbikes. It doesn't matter. All the images that have a window, we start there, and we hope. Then once we obtain these segmentations that you can see here, we jointly segment all the images of this target class, all those that have a bounding box. Now, the clever thing to do, I would say, the next step is to segment images of the same classes, but those images that do not have the bounding box. That makes sense, because now we can use as a source the images of the same class, which are now accurately segmented because we had the bounding box before. So now we segmented the airplane, we can segment the other airplanes in the same class by driving the segmentation this way. So now in the third stage, we can exploit semantic relation links and use this and this as the source pool together to segment the nearest neighbors in the ImageNet semantic hierarchies, which are the children and the direct ancestor of that class. So in the case of aircraft, you can have a jet, airplane, and a liner, and its parent may be transportation. So the source keeps changing as we move in the propagation process so that it contains the images that are most related to the target. That really helps. So we continue iteratively, we go down to the nearest neighbor in the semantic hierarchies until we segmented everything. So there will be a concept video here, which I was recommended not to play. That's exactly why I played. So I don't know how smooth it will look, but this took us so long to put together that I thought it would be a pity not to show it. This shows a bit the concept of the propagation. You know, you start by segmenting a small set of images which have a bounding box, and now we zoom out a bit, and you cannot quite see it. It will be a video, not a slideshow. And you keep propagating, and in red is what you segmented, in blue is the rest of ImageNet. And you can see as it expands like a wave out and colors the ImageNet segmentation. It looks so cool. This is actually the real propagation wave we are running. It's every dot you see is actually an image there, and you know, my student took like 3 days to do it. So now getting back to you know, this cool FX science. So how does it work? I said segmentation transfer. What do I mean? Right? What do I mean? You have a source pool of images that have segmentations. At any point in the algorithm, you have a target image. So we are going to try to transfer segmentation to help the target. How are we going to do this? We're going to sample windows on the target image, and of course these are objectless windows. This helps you to focus your resources centered on objects. There are also background windows, but because some of them are centered on objects, you get better spatial support. Then we're going to retrieve nearest neighbor windows from the source set, which sometimes are not from the right category. It doesn't matter. And now, this visually most similar window, we make the assumption that their segmentation mask is kind of similar to the segmentation mask of the target window, because we believe that similar appearance induces similar segmentation. And now you get this average segmentation mask from known the neighbors for this target window. You can reassemble them to propose a soft segmentation mask for the target image. So the soft segmentation mask basically asks a pixel. For every pixel you get a number in 0, 1 that indicates how likely it is to be foreground according to this process. And that's not yet a segmentation. Now you can use that initialization to initialize a standard grab cut algorithm. So you can get the appearance models for grab cut and allocation prior, and then these will refine you the segmentation and get here. So the important point about this process compared to previous works on label transfer is that it works at the window level, not at the whole image level. And this is really helpful because it makes more efficient use of the training data. Now it becomes translation invariant. So if your training images show a motorbike in the top left corner and you have one in the bottom right, it's still going to work. Also, it has compositionality. So it can assemble a scene with a cat and a dog next to each other, although maybe all the training images I found is something remotely similar to just a cat or just a dog. If you match entire images, it doesn't work as well. And of course, because single windows have less variability, they are easier to match than entire images. So the price to pay, so window level transfer is better than image level transfer, but the problem is now you got a lot of windows. So when we work on our scale on 1 million images with about 100 windows per image, you have 100 million descriptors, which are already 3 terabytes. So the distance computation between windows also becomes very slow. This is a lot slower than the first part of the talk, because the source set did not have a lot of windows, it had just models. So this becomes feasible, more than feasible, it becomes fast if you turn all your descriptor into compact binary codes by using some hashing method. So here we use the Gonga-Lazebnik method, which gives you a 200-fold speed up and 500 times smaller. So at this point, on a single core of a humble workstation, not a Google level workstation, you can get about 40 million comparisons a second, which means that even with a 10,000 image source pool, you can still segment a target image in just a few seconds. So this process is fast if you do it right. There is code available for this on our website. So this was the concept of segmentation transfer. What it does, it gives you this initial pixel level distribution of where the object could be on a target image. Now we are going to joint segment all the images of the target class jointly by sharing appearance models across them. And if we have a related class for which we already ran the propagation, so the propagation wave already reached the related class, we can use the appearance model of the related class as another term to help segment. In this case, canines would help dogs. And then you do the joint segmentation, you get these pretty results. So for this, we expanded the standard GrabCAD energy function to contain a lot more unary potentials. So the first, so here imagine you have two images of the target class. In this case, they are dogs. Through the segmentation transfer process, you got this pixel level map that tells you roughly where the object is. You can use it as a unary potential additional in GrabCAD. Then you can use this mask to initialize appearance models for GrabCAD, which you can use as traditional appearance model unary potential. You can take an appearance model that's shared across the entire class. This is useful because it's estimated over all the images, and therefore it washes out, averages out inconsistencies. And you can even have appearance models that you take from related classes that have already been segmented. So this is just GrabCAD with lots of unary potentials that come from the transfer process. And you have the traditional label smoothness pairwise term that everybody uses. Once you have all these unary terms, you can just run standard GrabCAD inference, which gives you a global optimal solution here. And from the solution, which is a binary segmentation, you can re-estimate the appearance models and iterate the two, just as in standard GrabCAD. So this is basically GrabCAD with tons of unary potentials. So having all these unary potentials I'm going to show helps the results. Makes sense because all these unary potentials import information from related classes. The problem is now we have weights to train. It always comes back to that, fun to throw everything in a kitchen sink, but then you gotta train it. So you have all these alpha weights. So what do? We train the alpha weights so that the segmentation accuracy will be maximized at the first iteration of the process. If you want to do it at the end, it's a lot more messy because you're estimating appearance models. So imagine you have fixed appearance models. At that point, the segmentation is basically independent over the test images, the training images. So we use a small set, which we annotated with about 900 images with segmentations, 90 images with segmentations. We use that held out set to train alpha on ImageNet. And we train it with standard structural output regression, which basically say you want the alpha weights so that the energy of the best possible configuration of pixels, so the best segmentation, that energy will be lower than the energy of any other configuration of pixels, any other segmentation. And it's fun because we can solve the inference problem exactly. You will also solve this weight learning problem exactly, although it has exponentially many constraints. Without going into details, this has been proven a long time ago by Sean Ardis and other people in machine learning. So you get the optimal weights, that's good. So now we get to results. Before we get to ImageNet, we tried the whole thing on smaller sets to see if it was working and to check that all the steps were aligned well. So here are some results on the Pascal VOC 2010 test set. So here the same classes are in the source pool and in the test set, so it should work. You don't even need to transfer anymore. So here is some examples of a test image and the transfer, the segmentation mask that, this M mask that comes out of the segmentation transfer process. And the result after GrabCAD, which works well even for objects that are off-center, and they are small. You can even find multiple objects. And you get reasonably accurate segmentation, so of course it's a bit blocky, like on the sheep here, because it likes very short boundaries. That's classic bias that comes out of GrabCAD, of the pairwise potential. So we also ran an evaluation, a quantitative evaluation on the Pascal VOC 2010 segmentations. And what we wanted to prove there is that if you would just do the segmentation transfer process with a single big window covering the whole image, that wouldn't work as well as doing it really at the window level. That we wanted to prove that this is really an advantage. So this line you see here, this is IOU, intersection over union of the segmentation mask, accuracy higher is better. This line here is exactly the whole process, but there is a single window on the whole image, if you wish. It's global neighbor transfer, and that's a lot below the results we get, a good, basically half what you get if you transfer at the window level. So that's a really important thing to do. And here are two unrelated methods by other authors, just to put things in context of the state of the art on this data set. So it is state of the art, and it's faster than other methods, and it's very, very simple, I would say. Download the code.
Have you tried the objectiveness measure as an initialization for your GrabCAD?
The objectiveness measure is not used as an initialization for GrabCAD, but it is used to sample the windows. The windows that are at the basis of the segmentation process, that are done for the nearest neighbor.
Have you tried it
as a baseline?
Just as a baseline.
Oh yeah, we tried that as a baseline. I'm sorry that it's not in here. That's indeed does quite reasonably. It's something like 25 or I don't remember it exactly. It's in the range of this, maybe 29. It's substantially below, and that makes sense because if you wish, this type of maps we get, it looks pretty much like the objectless maps I showed before, but they're not on all objects, right? They are on the objects that appear in the source pool. So you can see it as a subset of objects we fire on everything. That's an
So
object.
here you would see the stop signs and so on.
You would see, I mean, I'm sorry that everybody, but yes, you would get the stop sign. If it works correctly, you would get the stop sign. So if it works correctly, it should be worse. And here is some example from Grazzo 2 against small objects, etc. I skipped that. Let me come to the, so this experiment was only segmentation transfer from the source pool. We didn't have an element of joint segmentation over the entire set. So I'm introducing the elements one at a time. So now we tried to experiment on ICOSEG, which is a dataset that was designed for co-segmentation. And now we can start to play with, to check if the idea of segmenting together a set of images of a class, if that brings something. So here in this case, we can try the segmentation transfer and the class level appearance models. We cannot try yet the recursive propagation because we don't have a hierarchy here, but this comes in the next slide. So here we tried various variants, and I would like to send a take-home message. What is a good baseline? You forget about everything. You just take a box in the middle of the image covering 50% of its image, of its surface, and you use that box as your initial segmentation. And you pass it through GrabCAD. It's going to turn it around in its iterations. Well, that does damn well on this data set. Actually better than state-of-the-art 2010. And not that far from state-of-the-art 2011. So, you know, this is not to take anything away from previous works. We did a hell of a job in defining the challenge and everything, but proper baselines thought over are important. So this is a result where basically this model would be our image-only model. It's like GrabCAD, only having an appearance model per image. If you switch that off and turn on an appearance model only at the level of the whole set, you get close to a work by Batra that appeared. And that does about the same, a bit better. Now, if you combine the two, again, no transfer. You just have an appearance model for the image, an appearance model for the class, and you keep rotating, you already beat state-of-the-art. So that's very, very simple, no segmentation transfer, just go. And that's, for me, the baseline. We have to beat this, right? So if you just take an appearance model on the image, and you add our segmentation transfer process from the Pascal, there is no intersecting cluster, no elephants in Pascal. So that really now becomes a transfer learning type of thing. Then you get to a good result, right? About the best you can do from just a dataset. And now if you put it all together, you have an appearance model on the image, one on the class, and you do this transfer from the Pascal, then you get to a better result finally. So all the components of the method I presented are useful. So if you have transfer to anything, it helps. If you have a class-wide appearance model to anything, it helps. And it outperforms these two state-of-the-art works, and it's orders of magnitude faster. So the whole process is about a few seconds per image, as opposed to minutes or hours actually for this one. Download our code. So, so this was just sanity checks for me. We tried a data set where we could only do transfer, but not class level things. That Pascal. Now we tried something where you can do transfer and class level, ICOSEG. Now we go to ImageNet, where you can do class level models. You can do transfer and propagation. Propagation is just this idea of recursively transferring from what you segmented before. Now we get to the full Monty type of result. We see if it works. Here are some example results on Kangaroo. The last row is always a segmentation fault where it didn't work, and the previous 4 rows where it worked. And you can see, which animal is this?
Cat?
Maybe it's a wolf. I like to do this quiz unprepared, where I also don't know what the class is. It's not that easy. And here are some examples on man-made objects, and you can see the variation in appearance and scale and context. So all these results for 500,000 images are available on our website. So this was qualitative, and now quantitative. Now, how am I going to evaluate this? I started my talk by saying there are 0 ground truth segmentations. So am I going to just get off this without showing you any numbers? Well, I don't think so. Not at ECCV. So what we did is dive into a mechanical Turk, and we annotated about 5,000 images over 10 classes. It's not big. It's about 1% of the data set, but can at least tell something. And we took care of annotating images that are distributed uniformly over our propagation stages, so that we can look if the performance degrades over stages. Because as the propagation waves goes away from the ground truth data in Pascal, in theory it should get worse, because it's using its previous iteration as ground truth, so it should degrade. And in fact, that's what we can see. First of all, we do beat GrabCAD initialized from the image center, even on this easier data. Hot was close call. No, actually it's 6%. And this is the results on stage 1, and they are very, very good. It's almost 90%, but don't be fooled. There we had the ground truth bounding boxes to help us. Stage 2, now this is a real interesting thing, because now you had no ground truth bounding box. and you get to 77, about 76, 77, which is quite accurate. This is pixel level localization accuracy. And stage 3 just goes down a bit, stage 4 it goes down a bit, it keeps going down a bit, and on stage 5 it kind of crashes. But the good news is, at stage 5, we are so far from the source that we were not surprised, and also stage 5 there are very few images, because these are really the leaves at the end, so it doesn't compromise our average too much. So the message is, yes, it does work nicely, better than baseline, and transfer does help, and performance degrades gracefully over stages as you go away from your ground truths, you're propagating errors. This brings me to the last slide of this talk. I presented you, in part 2, an efficient scheme to recursively segment images in ImageNet, which basically uses its previous output as ground truth for the next. We combine ideas from all kinds of previous literature, segmentation transfer, co-segmentation, binary codes, structural output learning, you name it, throw it in. And we got state-of-the-art results on IcoSeg and on the Pascal VSC challenge, and the first results on ImageNet. So I don't know if you want to call that state-of-the-art. All the segmentations are on our website, and the segmentation transfer code and objectness are also on our website. Thank you for your attention. I'll take questions.
We do have time for questions, so both from, I guess, in the room and maybe some over VC, we can figure out how, if you yell, maybe. Let's start from the room.
So it looks like, if I understood correctly, you're transferring knowledge within ImageNet. It looks like you're treating children and parents the same way. Like you're transferring knowledge the same way. Is that a good idea if we treat them differently? Because they're fundamentally different. The subsets work differently.
Can you repeat the question from VC just for...
So Caroline suggests, first of all, she asks whether in our algorithms we are treating parents and children in the same way as siblings. Mm-hmm. And if so, could we do better?
Not as siblings, but you're treating parents and children the same as each other.
As each other, okay,
yes.
Sorry, thank you. And if could we do better by treating them differently? And so my answer is, in the second part of the talk, where we've transferred pixel level segmentations, they are absolutely treated identically. In the first part of the talk, it is different because there is only a single huge ancestor, which is all of the rest of the tree, from which we go down, godlike objectness comes down to help you, and location priors come down, and nothing goes up, So in that sense, it's asymmetric. Mm-hmm. And the alpha weights we learn hopefully compensate for the different level of uncertainty. In the second part, so there I don't know if we could do much better. The second part of the talk could be better. And in fact, why it could be? Because the children classes have lower appearance variability. The variance of the children classes must be smaller by the construction of the set. In fact, if you really look at leaves of ImageNet, you got, the white snake that lived in your grandma's house, and super tight. And instead of 3 levels high, you have the snake that lives anywhere. So in fact, it would be fun if we could adapt the weights of the transfer scheme or how many windows or whatever to take into account that there is lower uncertainty not uncertainty, lower appearance variance. We were thinking about doing that. We did not do that yet.
While you're on that topic, can you say a little bit about these alpha weights? Are these per class? Are they global for the,
So in the first part of the talk, when we were transferring bounding boxes, there are 2 trees in this project. The animal tree, the instrumentation tree, which is any man-made object. Right. We train alpha weights from animals, and the same alpha weights are used for all the classes of instruments.
I see.
And vice versa.
Okay.
Okay, and for the second part of the talk, it's more complicated because as you go with the propagation stages, we believe you need to change your weights. Because the relative importance of various terms in the GraphCut function should change as you go away from the source. For example, the image-specific appearance model probably become more important as you go away compared to the prior from the segmentation transfer. So there we trained a set of weights for every of the 2 trees and for every propagation wave stage. So stage 1 you have a set of weights, at stage 2 you have another set of weights, at stage 3. And they are different. And on IcoSeg, they are a lot different even. Like those on IcoSeg have really high weight on the class level model because all the bears are really very similar. The class level model of the ImageNet, it gets lower weighted.
Makes sense. More questions? Yeah.
It's not really a question, but more just an observation. So it seems like another measure of how easy something would be to segment could be how cluttered is the background. I don't know if you've thought of this or using sort of background clutter measure to solve those images.
What would I do with it as another source of knowledge?
At least with ones with bounding box, you can even just look at how cluttered is everything else.
Yes, I understand. Let's assume for a moment I could measure that.
Okay.
How do you propose to use that signal?
You could just prioritize those as you're doing these things in stages.
In the sequence. Yeah. Oh, that's fun. That's a fun idea. We never thought of this. And in fact, I also have a measure to measure how cluttered the background is, and the measure is objectness, because if you have plenty of stuff in the background that are objects, you get a high entropy of objectness. If you have an isolated object, you have a low entropy. So in fact, this is a good idea. Thank you.
So you had on the second part, you had a nice kind of build up of if you add this, you get that much extra in terms of the performance. Do you have a similar kind of breakdown for the first part? Like if you just did a global appearance model and then evaluated on the objectness windows, you get this. And you keep
Yes, I did have that in the first part. Maybe I went a bit quickly. I'm sorry. It was in the form of a big table. So what we did for every possible combination of source and type, you get one possible knowledge combo. For every single pair, we had a result on the whole, test set, and for every combination of pairs, every possible combination, we had another number. So we do know the contribution of the various bits and pieces. But what is more important, the take-home message, is that every single bit and piece helps. So we couldn't drop anything out. Some of them kill each other. For example, if you have all of the appearance models, bag of word and hog and surf, at some point the color one is no longer useful if you already have the hog, for example, but you cannot remove location, appearance, or context. All the three are helpful. You cannot remove the ancestor or the sibling. All of them are helpful. You can find a table in our paper and in this recording.
Great.
Any other questions? Yes, me.
Have you tried to extend the objectness to video?
Well, I wish I had recorded my answer to Rahul I gave on Monday. We have not tried, and the reason is only we don't have enough manpower. I have my students busy and plenty of stuff, and I should do that. It is going to be better. You can have a thought experiment. If you run it on every single frame independently, just stupidest video objectness ever. You run it on every frame independently, then you do some temporal integration. The frames for which objectness is kind of not quite sure, and maybe that was an object and the edges were strong, this is going to be washed out, and those windows were sure consistently over time. That's a classic temporal integration in video effect. It's going to be better, I believe. But we should go beyond that. We should have objects defined over spatiotemporal superpixels, also called G pixels, due to their author Matthias Grunman, who's sitting here in front of me. By the way, Google is listening. So during the workshop on Monday, the workshop by Uncle Rahul, I was get to know at the end of the workshop, we uniformly all agreed that the spatiotemporal superpixels that Matthias proposed in CPR 2010 are from now on known as the G pixels. Just to be sure, I'm on record. So we should do objectness on those G pixels, should be better.
And there you have it. I think I can't think of a better way to end this talk. Thank you again, Vito.
Thank you for having me.
VC Ops, please end the recording.
Bye.
I'm going to get sillier from here.